Welcome to The Explainer. Today, we're unpacking something absolutely mind-blowing. The smooth, continuous space you're sitting in right now, the fabric of reality you literally move through every single day. It might actually be a mathematically perfect illusion. We're looking at unified dynamics to figure out how a rigidly pixelated universe at the tiniest scales can flawlessly masquerade as the smooth space-time we know and love. Let's get right into it.
Okay, let's dive into this because this question really frames the ultimate paradox in modern physics right now. See, Einstein's general relativity absolutely demands a smooth, continuous space-time manifold. Without it, gravity simply doesn't work. But then, you have frameworks like unified dynamics arguing that fundamental reality is actually this discrete, rigid network of tiny geometric shapes, specifically interacting K4 tetrahedra. So how on earth can both of these things be true at the same time?
Well, here is our roadmap to figure that out. We're covering discrete reality versus smooth space, the S3 cubic shell, the 18 transport directions, flat-limit normalization, and finally, the illusion of the continuum. This agenda is going to guide us right through the mathematical magic trick that actually solves this problem. Starting off with Section 1, discrete reality versus smooth space. Let's set the stage for this massive contradiction.
So, here is the core conflict staring us in the face. If reality is truly rigid and pixelated up close, built from this underlying network of K4 tetrahedra, how does it somehow average out to perfectly smooth spacetime at our human scale? And even more crucially, how does it pull this off without breaking the universe's absolute speed limit, Lorentz invariance? I mean, if you have a rigid grid, moving diagonally should technically look and behave differently than moving straight along an axis, but in our universe, it doesn't.
To bridge this massive gap, physics uses a mathematical tool called the Vierbein. You can basically think of it as the ultimate mathematical ruler. It maps the messy, curved coordinates of the universe into a locally flat, smooth Minkowski tangent space. In unified dynamics, the big hurdle, which we call gap G1, is proving that we can construct this perfectly smooth Vierbein ruler natively out of those jagged, discrete tetrahedral pixels. And the concept of coarse-graining perfectly illustrates how we solve this. Think of a 4K TV. If you press your nose right up against the screen, it's just a rigid grid of jagged red, green, and blue pixels, right? But step back, and your eyes naturally average it all out. The microscopic mess completely vanishes, leaving a perfectly smooth image. Well, in physics, coarse-graining does the exact same thing when scaling up from the microscopic geometry to macroscopic space.
Moving on to Section 2, the S3 cubic shell. We're stepping into the theoretical lab now to actually build the geometry that bridges this gap.
Let's build this thing from the ground up. Step 1, we start with a central three-pronged quark core resting right on our local X, Y, and Z axis. But this shape has exposed boundaries, and as we know, nature absolutely hates open boundaries. So, step 2, the math forces it to recruit exactly 6 surrounding vacuum tetrahedra to cap those exposed faces. Which brings us to step 3, the whole structure perfectly encloses itself into a sealed 3D volumetric cube. We call this the S3 cubic coarse-graining shell.
Now, that number, 6, is definitely not random. A standard Euclidean cube can mathematically be sliced into exactly 6 congruent, non-regular tetrahedra. These correspond to the 6 mathematical permutations of our 3D axes, known as the S3 permutation group. So the central quark core is literally acting as a geometric backbone, forcing the surrounding vacuum to organize into this flat cubic space. It's like a giant puzzle, and the pieces lock together perfectly.
That brings us to Section 3. The 18 transport directions. With our cubic shell built, we need to map out how things actually move through it.
And the magic number here is 18. Around any central packet in this cubic lattice, there are exactly 18 local, unaveraged, discrete transport directions. These are essentially the physical wires along the edges of our tetrahedra where information and energy are actually flowing. We can break those 18 directions down to see what's really happening. First, we have 6 axial channels. These are your straightforward, orthodox paths. They move in straight, orthogonal lines right along the coordinate axes, up, down, left, right, forward, backward. They're just cleanly connecting the faces of our geometry. That leaves 12 shear channels, and these are the messy ones. They're the diagonal transport paths moving along the edges of the structure, cutting across the corners of our cubic shell. Remember that problem with Lorentz invariance we were just talking about? Yeah. These diagonal shear channels are the exact culprits that threaten to ruin the smooth symmetry of space.
Which brings us to the real climax of this explainer, Section 4, Flat-Limit Normalization. This is where the math pulls off a truly spectacular disappearing act.
Now, what's really fascinating about this is the exact cancellation that happens when we average these paths out. When you calculate the tensor product of those 12 messy diagonal shear channels, something totally beautiful happens. Because of the strict parity symmetry of the cube, the equal balance of positive and negative directions, every single off-diagonal cross term completely annihilates. A positive 1 times a positive 1 is perfectly canceled out by a positive 1 times a negative 1. All those messy diagonal movements literally sum up to 0, just gone.
So let's look at the mathematical components that actually survive. The 6 axial channels give us a straightforward yield of 2 delta. The 12 shear channels, now completely stripped of all that diagonal messiness, leave behind a purely diagonal footprint of 8 delta. When you add them up, the total, unweighted transport average perfectly balances out to exactly 10 delta.
So the crucial takeaway here is this geometric verdict, 10 delta. Because all that off-diagonal shear vanished completely, the resulting mathematical structure is perfectly proportional to the Kronecker delta. And in the world of geometry, the Kronecker delta is the literal, exact mathematical definition of the Vierbein, our ruler for smooth, orthogonal, flat space. We just built it from scratch.
All right, let's head into our final section. Section 5, the illusion of the continuum. What does all this incredible math actually mean for us?
First off, gap G1 is officially closed. The Vierbein doesn't have to be blindly assumed as some fundamental magical property of the universe anymore. We derived it natively from the discrete network itself. Lorentz invariance is perfectly preserved at macroscopic scales. Physics absolutely doesn't have to break its own rules to get smooth spacetime out of a pixelated Planck scale background. Smooth space is literally just the symmetry-averaged flat limit of those 18 discrete channels perfectly balancing each other out.
This whole concept is so perfectly captured by a canonical quote from Captain Cato in the Unified Dynamics material. The field is the zero. The dynamics is the recursion. The physics is the fixed point. Think about that. Our physical laws, even the smooth space we exist in, are not the base reality. They are simply the stable fixed points, the inevitable, balanced results of this underlying geometric recursion constantly happening at the microscopic scale.
It really shifts your entire perspective, doesn't it? If the smooth space we take for granted every day is just an elegant optical illusion created by perfectly balanced microscopic geometric pixels, what else about our macroscopic reality is just a mathematical trick waiting to be decoded? Keep questioning the fabric of reality and keep seeking those answers. Thanks for hanging out with me on this explainer. I'll catch you next time.